Okay, an inner product is a rule for combining two vectors. Now we're going to write inner product with a pointy brace here and a pointy brace here and the two vectors inside. Okay. Now, an inner product is like a dot product in many ways. It has the same formal properties as the dot product, so that the properties of an inner product are analogous to the properties of the dot product. So we're going to define an inner product by this rule. Now, U is going to be the vector U1, U2, V is going to be the vector V1, V2. The inner product of U and V then is going to be C1, U1, V1 plus C2, U2, V2. Now this is very much like the dot product. If the C1 and the C2 are both 1, then it is the dot product. It's just U1, V1 plus U2, V2. But we're going to let C be fixed numbers. We're going to let C1 and C2 be two fixed numbers. They're going to be the same numbers for any instance of this particular inner product. Now there are more conditions that we have to have on C, and we'll see why there have to be. If we don't put those extra conditions on it, we don't have an inner product. Okay, well the first I don't even know what that second word is there. Oh, okay, it's analogous, just the rest of the word. Okay, I'm sorry. Okay, so U dot V equals V dot U, one of the fundamental properties of the dot product. And we understand why that is. Okay, the analogous property of the inner product would be that the inner product of U and V is the inner product of V and U. Can we prove that that's the case for this particular rule? Well, yeah, it's pretty easy to prove. The inner product of U and V is just what we wrote up here, so here it is again. The inner product of V and U, however, V and U are in the opposite order. So now, when we multiply C1, we multiply it by the first component of the first vector. The first vector is now V, so it's going to be C1 times V1. Excuse me, and then times the first component of the second vector, which is now U. So we're going to get C1 V1 U1 instead of C1 U1 V1. Okay, now of course we understand that this is the same as this by the commutative law of multiplication, but we can't simply say, well, that looks like it ought to be commutative because everything's commutative. Well, matrix multiplication isn't commutative. There are lots of things that aren't commutative. So we have to be very careful, and we have to write it out very carefully, very precisely. Okay, well then we do the C2, U2, V2, but now we've got V as the first vector, U is the second, so it's going to be C2, V2, U2. Well, by the commutative law of multiplication, we can easily show that these are identical, so that this property holds. So I could put a check mark by this property. Okay. Now another property is that when you do a dot product of a vector with itself, it's greater than or equal to 0. And furthermore, I didn't write it down here and we didn't do it, it's only equal to 0 if the vector U is the 0 vector. And that's something you might well have to prove. Well, the question then is the inner product that we've defined up here always greater than or equal to 0? Well, what do we mean by the inner product of U with itself? Well, the inner product is C times the first component of the first vector plus the first component of the second vector. Here, the first and second vector are both the U vector, so the first component of this one is U1. The first component of this one is U1. So we have C1 times U1 times U1. And then it's C2 times the second component times the second component. Well, C2 times the second component of the first vector, which is U, so that's U2. And the second component of this U is also U2, so we have C2 times the second component of the first vector times the second component of the second vector. And of course, that's C1 U1 squared plus C2 U2 squared. These are not necessarily greater than or equal to 0, are they? I mean, if you read the extra conditions I put on to C1 and C2, they are. But before those conditions are imposed, and I haven't mentioned those conditions yet, even though you might have read them, if it's just plain old any C1 and C2, then if either one of these, C1 or C2, is 0, we could find, if either C1 or C2 is negative, then we can easily find U1 and U2 that make this negative. For example, if C1 happens to be negative, just let U1 be anything but 0, and let U2 equal 0. That'd be perfectly good vector U, the vector 1, 0, for example. Well, C1 is negative, that's going to give you a negative, isn't it? So if either C1 or C2 is negative, we can select out the U1 and the U2 to make the inner product negative, so the inner product is not always non-negative. Okay, so I say this is not negative as long as neither C1 nor C2 is negative, okay? Well, that's not exactly what I just said. What I just said is, if either of these is negative, we don't have an inner product, okay? If neither C1 nor C2 is negative, then, well, neither of these can be negative because U1 squared is not negative, U2 squared is not negative. Okay, so that if neither C1 nor C2 can be negative, there's no way this result could be negative. And then we have satisfied this property of the inner product. I did go on to say what I said before. If either of these is negative, however, there is some U, and actually many U's, for which the dot product would be negative. So we add the condition on C1 and C2 that at least one of the two has to be positive and that neither be negative. Now, why does at least one have to be positive? Well, we haven't gotten to that property. The property that the dot product is equal to 0 if and only if U is equal to the 0 vector. Okay? And that will be related to the condition that I placed on here that at least one is positive. And I will say I haven't proven that condition. I haven't proven all the conditions necessary for an inner product. I've proven two of the main ones. But with these conditions, this will satisfy all the conditions of an inner product.